to thank everyone for coming to our newest seminar series from GeoDAWG, which will be given by Donglai Ma today. Last week, we had a really good talk by Tim Kodikara. And this week, we're really excited to hear about Donglai's work on the radiation belts. I just want to let everyone know that the seminar series is being recorded, and we will make sure that that recording will be uploaded to our YouTube site, and then we will link that recording under Donglai Ma's name on our seminar website. So be sure to check back there, and you can rewatch this the video recording at any time in the future. If you haven't already, please sign up for our GeoDAWG mailing list. We have over about 120 subscribers to it, which is a very good community being built, and we're looking forward to kind of proceeding that in the future and sending some things out there. And then our next seminar will be given a month from now by Lucas Tarr and James Leake, transitioning a little bit to some of the work doing some data comparisons for the solar at the sun. So without further ado, I'll hand it off to Anthony, who will introduce Donglai, and will kick us off.
Hello, everyone. Welcome back. Just a quick reminder, if you come in, please make sure you're muted, and then only unmute if you're asking a question. And feel free to ask questions during the talk today, and we'll find a good time to interrupt Donglai and get your question to him. So either raise your hand or put it in the chat, and we can ask questions throughout the presentation. So as we've said already, today's speaker is Donglai Ma. He is a PhD student in space physics at the University of California, Los Angeles, in the Department of Atmospheric and Oceanic Sciences. And he'll be telling us today about machine learning models and data-driven methods of radiation belt dynamics. So thanks, Donglai, for talking to us today, and go right ahead.
Thank you, Anthony, for the introduction, and thank you, Adam, for the organization. Let me share the screen. Could you guys see the screen right now?
Yep, looks great.
Perfect. So hi, everyone. My name is Donglai Ma. I'm a third-year PhD student in Professor Jacob Bortnick's group in UCLA Space Physics team. It's a great pleasure and honor to talk about some of our group's recent study about machine learning models and data-driven method of radiation belt dynamics in this seminar. I'd also like to thank my advisors and collaborators from UCLA and CU Boulder, including Van Allen probe team and Space Weather technology team. So this is my outline. I'd like to start with a brief introduction to the Earth's radiation belt dynamics, and then discuss some of recent results from our group about modeling radiation belt dynamics. I will also talk about this new data-driven method of PDE discovery, which has not been used in space weather application. At last, I would like to summarize our findings and talk about our future work. Welcome to bring up questions throughout the presentation. Okay. So as we know now, the radiation belt electrons range from tens keV to tens MeV, which are known hazards to satellites. And they are extremely dynamic, as shown in this movie and this plot. Okay. You can see the electron flux variation based on the Van Allen probes data. For those who are not very familiar with Van Allen probes, they consist of two satellites flying in and out and get the measurement from 2 Earth radii to about 6 Earth radii. So the complex radiation belt dynamics is delicate. Is a delicate balance of various source and transport and loss processes. And it's worth to mention that energetic electrons in the radiation belt is basically collisionless due to their extremely low density. So one of the most efficient ways of changing their dynamics is through wave-particle interaction. in the magnetosphere, there exists a variety of the plasma waves, which can affect the radiation belt dynamics. Here, I'm showing the spatial distribution of the various waves in the equatorial plane. Those waves, including electron-ion cyclotron waves, as well as Higgs waves and Chorus waves. So as we can see, when the electrons are trapped in the Earth's radiation belt and drifting around the Earth, they can interact with various plasma waves and change their dynamics. So I'd like to briefly talk about the source and the loss mechanisms. In the previous year, electron injection together with inward radial diffusion were considered to be the primary mechanism of driving the acceleration in radiation belt. However, in recent satellite observation, it has shown clearly that there exists a growing radial peaks in the heart of radiation belt, indicating that there are some local acceleration is going on. And it's been discovered that this acceleration is driven by Chorus waves. And regarding to loss mechanisms, if there is an increase in solar wind dynamics pressure, it will push the magnetopause, and the electron which trapped in the magnetic field would drift out and lost from the heart of belt. Another important loss mechanism is this precipitation loss, which caused by various waves through pitch angle scattering. To understand and predict this radiation belt dynamics, the traditional approach involves integration of the Fokker-Planck equation. In this kind of model, the wave-particle interaction are treated as a diffusion problem. So in order to run the simulation, we need to know the boundary condition as well as the initial condition. We also need to know the diffusion coefficient of different waves. So the shortcomings of this kind of model is that it's based on quasi-linear assumption, and it's not easy to get those coefficients when we're dealing with some unknown physics. And it's usually only took a small period of time of the observation to compare with your simulation. But the total information in all the observation is not being well used. The simulation would also be easily failed when the quasi-linear theory is not appropriate. So the overarching question and the major goal of our study is this: how could we extract science from all the radiation belt data? More specifically, we want to answer those two questions. Could we build a model to describe right dynamics and combine our physical understanding, which already exists? And is that possible to directly get unknown physics from data? So the first product of our research is a machine learning model of electron flux. Since the amount of satellites are exploding nowadays, with tons of satellite measurements, nowadays we could easily create machine learning models. And we want to have a model that could produce this similar result measured by one probe when we don't have satellites. And in this study, we just use a simple fully connected neural network, which successfully achieved this goal. So instead of talking about the familiar neural network, I would like to talk about these 4 questions, which are found out to be very important to achieve the good result in our research. What kind of data we can use to build the model? What kind of input parameters should we use? How to train and validate our model? And can our model reproduce results with physical meaning? So the first thing is data, right? The 1 probe instrument for electrons basically consists of RAPS and MIGAS. The 2 instruments have different energy range. For MIGAS, it has swing range. For low level, less than 200 keV. For medium value is from 200 keV to 1 MeV. And for high energy range is larger than 1 MeV. For wrapped channel, it's usually larger than 1.8 MeV. And in this study, the data we use in wrapped is 1.8 MeV to 4.5 MeV. And we didn't use high energy range in MIGAS because it's been covered in wrapped. Here I'm showing the MIGAS data we used in this study. The x-axis is the time and the y-axis is the L shell. You can see the flux variation throughout the whole mission of one element probe. And it's worth noting that MIGAS data has different versions. There is a background corrected version shows in these 3 panels for 235 keV and other hundreds of keV channels. Because the background corrected version, they were made to remove background contamination effect due to high energy electrons that produce Bremsstrahlung X-rays. But these data only available in several energy channels on both satellites. For lower energy channel, for example, this 54 keV, we use the original version since the corrected data is not available for now. We use Omni dataset as a module input parameters. I will talk more about this later, but those parameters are going to be the driver of our electron flux model because it contains most of the information in our magnetosphere. Regarding to the input parameters, we use SOLARWIND and GeoMagnetic indices history as the input parameters because we assume those parameters could represent the dynamics happen around the Earth. But the question is, how long exactly of the history we should use? It requires our physical understanding and the observation. Here, I'm showing the results from Seth Cloudpier, that's also a group member in our group, for the estimated electron decay lifetime in the radiation belt. As you can see for electron flux here, an enhancement happens, and then it will decay for the next few days if there is no another injection or something like this. As you can see, for the energetic electrons in radiation belt, for different energy channels, we could estimate their decay time, but their decay time is not the same. And this gives us a reference for choosing the length of input parameter histories. For example, if we want to get the electron flux at the time indicated by this line, we use the moving average of time history Omni index, which we selected as the input. And those input are identified here by red lines. Here I'm showing the final time history length of input Omni dataset we use in our study. For lower energy channels, you can see the length of history is shorter. And as we increase the energy channel, the length increase. One important thing is that not all the Omni parameters are used for our electron flux model. So choosing right parameter is very important. Here I'm showing our working flow example for channel 235 keV, like how we choose the final parameters we put in the machine learning models. We start with each of the parameters as the input and train the model. So it's shown in figure in this figure. Oh, sorry, in this figure. So you can see for each index, we use this as an input parameters, and then we compare its performance on the test data set. In this case, the best performance is AL. Then we repeat this process. The model is trained using the time series of AL and another input parameter from the Omni database. And then we keep repeating this process until the performance stops increasing. In this 235 keV channel, the first one is AL, and then AL and the pressure, and then AL pressure and CMH, and finally these 4 input parameters are selected for the machine learning models. The input parameters we select are also consistent with our physical understanding, because we are, as I described in previous slides, we already know the SOLARWIND parameters can drive the radiation belt dynamics. And after we finished all the channels from different energy, we found that basically all the models result input parameters are basically the same, including SOLARWIND parameters and CMH and AL or AE index for the geomagnetic index. We still have something left I want to discuss, which is really important when we train our model. Regarding to train process, you must have heard of this. Randomly split data into training and validation data set and test data set, train the data set on, and then evaluate on the test data set, something like that. But in this case, we cannot directly do this because our target value of electron flux is 5 minute or 1 minute resolution. And remember, for the input parameters, we have a long time history. We do a moving average of our time history. So if you randomly split your data, it would look like this. Actually, you are not splitting the data set. All your test data set would be included in the training data set, causing a data leakage problem. Another thing is, can we take a whole year out as a test data set? We actually can, but we choose not to. The reason is that if you think about this 1 year data set and compare it with other years, you could find, oh, this year it has low activity. And imagine if you took, in this year, there is no storm, there is no other activity. You will never get a good result because it can not represent what happens throughout your whole data set. So what we did is that we grouped our data sample into several days. Instead of choosing random, selected randomly or yearly, we grouped it in the small bins. And then we randomly split the data as groups into training and validation and test data sets, and make sure that the data samples in same time are in same data set for both A and B satellites to avoid data leakage problem. After we decide the model input parameters, we could tune the input length or trying to find the best input time history with a 5-fold cross validation. You can see there for different channels, and this is error, this is the R-squared value, which is the correlation coefficient. You could always see that the our cross validation help us find the sweet spot for performance and time lapse. We also use Optuna, which is a hyperparameter search tool to automatically finalize our model structure. For example, you could build a neural network model without telling its units, like how many neurons in each layer. You just tell him like how many layers I want, what's the range of layers I want to check, maybe like from 0 to 3, what's the units for each layers, maybe from 0 to 500, and it trains the model in hundreds of times. And finally, you could compare your result and get the best performance of the model. So here comes our results. We show our results on 2 out of sample data set. We choose 2 different lengths data set. The first one is in March 2017, where a storm happens. The second one is after 2018, where we don't have AE or AL data from Omni data set. So here I'm showing the result of 1.8 MeV. The model are calculated along the trajectory of 1 probe So here is the model observation. Here is the model's result. And here we calculate the equatorial plane's result. You can see the model successfully captured the right dynamics. For example, due to magnetopause shadowing and subsequent outward radial diffusion, when the solar wind pressure reached a maximum, the relativistic electrons were lost to the data. And the enhancement region is around L about 5, which is same with the observation. And you can see the relativistic electrons decay can be reproduced as the electron flux slowly decrease at both heart and edges of the outer radiation belt during late recovery phase. And here I'm showing the MIGAS results. The left one is 235 keV channel. The right one is 597 keV channel. Similar plots with previous one. You got those are the activity or the input parameters. Here are the observation values. Here are the model's results along the trajectory. Those are the flux values along the trajectory, and the final one is the result on the equatorial plane. You can see our model successfully reproduce the result of drop plot and the enhancement and decay. And one interesting thing is that for different energy reaction, its reaction to the time is reaction time to the storm is different. So high energy usually responds later than the lower energy. And you can see it's clearly reproduced by our model. So you can see here the enhancement after this storm maybe is around a few hours, but for this lower energy, it responds instantaneously. And again, these are the out of sample data set, which has never been used in training process. Another physical interpretation of our model is that since the velocity of the electron drift motion around the Earth is energy dependent, the global electron distribution following storms and substorms is expected to show an energy-related variation in MLT. This energy-dependent distribution results from a computation of the electron drift period and the loss time scale for that particular energy of electrons. For relativistic electrons, the drift period is very small because its energy is very high, right? And the loss time scale is large. So the drift motion dominates. And the fluxes are almost symmetrical in MLT about the Earth. However, at lower electron energies, the energy-dependent magnetic drifts are far slower. The drift periods are longer, and the loss time scale are shorter, such that the electron fluxes can vary dramatically within a limited range of MLTs. Here I'm showing an animation and the plot of our model results for different energies. You can see our model successfully reconstruct this physical understanding. If you focus on 54 keV, you can see that at the peak of geomagnetic activity, the electron flux shows significant MLT asymmetry in the electron flux enhancement. I'll show that animation again. You can see here, you can actually see the electron flux drifting around the Earth. Okay. We also cooperate with industry, the space environment technology team, and put all our models available online as the product. As long as we got the input parameters, we could reconstruct the electron flux for different energy channel at any location. Here I'm showing the test results using predicted AL index from CO Boulder. Because as I said, after 2018, we don't have AL index. But since we have the predicted AL index, we could see the model still captures the dynamics accurately, including the impenetrable barrier and enhancement and drop-off. Notice that those white like missing data is because we don't have predicted AL at that time. So if we got different models of predicted DST or other index, we could even predict the electron flux a few days ahead. And right now we have NLU models and anomalous DST, which could give us a 6-day ahead prediction. Here I'm showing our product with space weather technology team. And you can see that from anomalous DST I showed here, they have a prediction like a strong storm within 6 days. And remember, we got this plot is on November 3rd in 2021. At that time, we don't know what's actually happened about others like real dynamics in the radiation belt. But with this predicted DST, we could make an estimation of this 2.35 keV electrons. And you could see it's captured this enhancement in the radiation belt. And after a few days, when we got the real DST, we reduce the calculation, and you could see that the model's prediction is actually very accurate. And it's similar to the result happens here. With all those index, we could also reconstruct the radiation belt in old times, where we don't have 1N probes. In this case, we reconstruct the electron flux in 2004 and 2008, where we got the SEMPAX satellite, which is in a polar orbiting low Earth orbit. It also measures the electron flux, but it cannot get a near equator flux very accurately. But we could compare the trend and use that to validate our model. The results of this 2 months and this 1 year results both tells us that our model has a great performance and agree with the trend of the measurement. And it proved that our model can be used to reconstruct the radiation belt dynamics. So short summary for the first part of our machine learning models, we create an electron flux model using only SOLARWIND data and geomagnetic indices as input parameters, which could successfully reproduce the radiation belt dynamics. Our model captured the low energy flux MLT dependence, captured the drop-off and enhancement and other typical dynamics happened in radiation belt. The model performs very well in out-of-sample data set and could be used in reconstructing and predicting radiation belt dynamics in the future. And here are the 2 papers related to our products. Any questions for now at the first part? Let's see. Okay, otherwise I will continue. So remember, the second thing I want to ask is that we try to answer, could we directly get some physical understanding from the data? In reality, all the dynamical system, which is a great way of describing different systems like physical systems, biological systems, like really anything that changes in time can be described by dynamical system. If we have access to these dynamical systems, the set of ODE or differential equations or partial differential equations, then we could do a lot of things with these dynamics. Take some simple example in our area. We could do plasma simulation based on velocity equation, integrate particles through potential field or background field and get the result. We could study phase-space density evolution in the radiation belt and get the result. We can study fluid dynamics based on Navier-Stokes equation. So lots of things we can do if we have the dynamics. But in many systems, like in climate, in space weather, we don't always have access to exact differential equations. For example, as we mentioned in the shortcoming of Fokker-Planck modeling, the real Fokker-Planck equations not only have this radial diffusion term, but including many different terms like energy, pitch angle, mixed energy, pitch angle diffusion, or sometimes in fluid dynamics, you know how to describe the system, but your function is multi-scale. You write the dynamics in large scale assumption, but sometimes smaller scale terms will pop out. For example, like turbulence. It makes things difficult to study. So what we are going to want to do is to describe these dynamics directly from measurement data. And that's where this sparse identification of nonlinear dynamics algorithms comes in. This work becomes well known from this paper, Broughton et al. This group is in University of Washington, and it's become well known after 2016. I will show you how this thing works from this toy model. So we have the equations here. Assume we have the equations here for the three variables x and y and z, and remember here rho and beta are the constant. So this is a Lorentz system, and in some sense, we have linear terms. Okay, it's here, and we have nonlinear terms showing here. So in some sense, that these equations are relatively simple out of a possible right-hand functions that have specific form of a few active terms. And the nonlinearity like xy, xyz, xz, something like that. So what they do is they run the simulation of the system and collect the measurement data from real experiment. They collect the data in two vectors, x, y, z, so going down in time like this, and also x dot, y dot, z dot. That's all their measurements. And remember all the possible right-hand terms functions that these dynamics could take that tends to be quite sparse. When I say sparse, I mean sparse in the space of possible right-hand side functions. So right now, what we do is from our data, x and y and z, we construct vectors of all possible polynomial nonlinearities up to order 5. So for example, now we have 1 for every time is 1. For every time step x, we measure the x, we got the measurement of x, we got the measurement of y, and for x squared, we just calculate it. Okay. For other nonlinear term, we just calculate it and construct this big matrix, and so on and so forth till the like the limitation we set for this system. In this case, is order 5. And what we are going to do is we apply some kind of regression to find which combination of these nonlinearity terms represents this x dot, y dot, z dot the best. And remember, all we did is just from this data. We don't know what's this Lorentz system, like the exact function is. So what we do is we start with sparse regression to find the linear combination of the fewest columns of this library, theta of x, which are needed to describe x dot, y dot, and z dot. And there are many ways to do this regression, like lasso regression. So the lasso regression I showed, the idea is here. We add an L1 penalty in the loss function, which could be proved as the same formula here. Now it's easy to understand that if you want to find the minimum of your error function, but your beta is limited in this diamond because you add an L1 penalty. So your result would be at this vertex of the diamond, which means the result will be sparse. And if you just did least square regressions, you would get a little bit of all these columns in the fit. Okay, that's not what we want. So we use a sparse regression so that the model will do its best to give you a sparse result. In their paper, they use another way called the least square threshold algorithms. Well, actually, the purpose is the same. Now you could get the identified system purely from your data, which is pretty close to the real one. Okay, you can see the results is here. Now let's give it a little summary. So we got the measurements. We established the library based on the measurements, and then we do the sparse regression, and then we reconstruct our result of this function describing our system. And we are going to use this in the relation belt modeling. Since the electron flux dynamics could be described by phase space density of electrons, so we want to see, could we directly get the function from other dynamical system, for example, like in our dynamical system? And the answer is yes. Here, imagine we got the measurement along the Van Allen probe's trajectory. So this is the time, this is L shell, the Van Allen probe is flying in and out. And we collect some simulated phase space density results on this trajectory. The result comes from a Fokker-Planck equation, which I showed here. And we could successfully find this PDE only from those measurements we got. And notice here we introduce a method called integral formula to reduce the error when we calculating that library. Remember, when we calculate the library, we need to calculate the differential term, for example, like first order, second order, partial f, partial L, partial f, partial L squared, something like that. And it's always will introduce some error because our data is not on a well-conditioned grid, right? It's collected from the trajectory. Okay, so it will introduce some error. The way we reduce this error is by this integral formula integral formula. So previously, when they calculate the differential terms, they calculate on the single points. But in this case, we calculate a few points over small volumes. And in those volumes, when you calculate the differential terms, you integrate over it. So the error of the derivative will be canceled out. And you can see we do the experiments here. Without the integral, the result is not good. But with the integral form, you can see we successfully discovered the UX term, which related to this one, and partial U, partial XX, which is partial F, partial L squared terms, which is this one. And the coefficient is the same with the simulation. The more often and more interesting situation when the radiation belt goes through high degree of spatial temporal variability has been studied for decades, because understanding the mechanism's response for the acceleration and the loss of electrons is essential for predicting the response of radiation belts to geomagnetic disturbance. So it's worth to mention that our method could also be used to identify the source and the loss region in the radiation belt. Here, the simulation of the Fokker-Planck equation, we also add the source and the loss region. And the PDE find method successfully identified the source region and the loss region with their strengths. So here, if you could see source region is a constant, which shows here. And for the loss region, we use an F to describe it. And F in this case is U. It's successfully discovered. For more details about this algorithm, I refer to this paper written by Rudy. It's the same group in Washington University, data-driven identification of parametric partial differential equations. And one important algorithm they use is group sparsity. But all those PDE discovery methods requires a well-conditioned data set on the grid. Well, when I say well-conditioned, it means the data on the grid. So you can calculate the differential of those terms, but not those sparse sampling with a lot of values we already got from space satellites. But we do have a machine learning method that could reconstruct the data set, as I showed in the first part. Recently, our team member, Adam Kellerman, comes with this well-calibrated data set with 36 spacecraft of phase space density. And with this data set, we could easily build a machine learning model like the previous electron flux model. And this will not only just be a phase space sensing model for people to use, it could help us to reproduce the phase space density under different dynamics with high quality and resolution, so that we could put this phase space density under different dynamics and then contribute all those output well-conditioned data into our PDE discovery method. To make a summary for our future plan, we want to use our data set to create a machine learning model, which we already did for the electron flux. It's very similar. And then we want to generate a phase space density data set, but it comes from the real data. But one good part is that we can generate a well-conditioned data on the grid, and then we can put it into our algorithm. So we'll find, okay, what's the real result? What's the real function governing the radiation belt? Is that different from our previous understanding? Is that missing terms in our function? Well, it's going to be explored, and this is our future plan. Thank you all. That's all for my presentation, and happy Lunar New Year. Welcome to any questions.
All right, thank you, Donglai. That was a very interesting presentation. It's a lot for me to think about, at least. Do you have any questions from the audience?
Anthony, just a quick question, probably more so of clarification. Earlier in the talk, when you're talking about your machine learning process, you discussed radiation belt losses due to magnetopause shadowing. I was wondering, is your model also capable of trying to look at losses due to precipitation at all, or is that not something you can look at?
This is a very good question. So we don't know like precipitation happens or not. All we know is that some activities like could introduce precipitation loss, but it's hard to identify it in this kind of model because we don't have pitch angle scattering or a specific wave. But it's the next step for us to compare our model results with wave activity to see, okay, where is actually precipitation happens, where actually is magnetic shadowing effects cause the loss process.
Awesome, thanks. Yeah, I'd be really interested to see what comes out of that.
Thank you.
To sort of follow up on that question for the second half of your talk, when so it's my understanding that you need to sort of predefine which combinations of variables you're going to allow the system to try and
Yes.
give weights to, right? So how difficult would it be to sort of create an analytic function that could capture something such as energy dependent loss through precipitation and those kind of things? Is that difficult to do, or?
Oh, it's actually, well, in Fokker-Planck equations, they already did similar stuff. So that's the first thing. And the second thing is, I didn't put this in this presentation, is that as the development of this PDE discovery method, they could identify the dynamics under some coordinates that we don't know, that we don't need to define these coordinates. The method could help us define, okay, which is the coordinate we should use.
I see.
As long as we got some, for example, like a adiabatic coordinates, but it could cooperate it with all or like slightly transform your coordinates under some, if you put a lot of data into it. So that's the good part of this PDE fund survey. But as I said, like we already have some physical understanding of, like, for example, like Fokker-Planck equations. So it's easy to, I think it's easy to build these coordinates regarding if we want to study precipitation process or other process.
I see. Very cool. I also had a question from earlier in your talk on how you chose the history length to use for each energy value. And I think you showed a plot where the accuracy got worse with a larger window. Was that right? Yeah. Do you know why that might happen?
Yes. So the thing is, for this kind of training process, we fixed the model size, like model structure. For example, like let's say like 3 layers, 200 neurons, something like that. So if we like increase the length of time history, and the model performance is not like increasing, it's perhaps because all those extra information we add, for example, after 10 days, the next 10 days we add is not useful to our model, right? And because our model size is restricted, so it will cause some like decrease for the model performance. Maybe like if we go to 30 days, it would like it would look like maybe like a straight line or a slightly go ahead. But we find that sweet spot that, okay, it's already got a good performance and enough to cover the dynamics.
Any other questions from the audience? I had one more actually, if no one else has something. Is earlier on you were talking about the energy ranges that you use from different instruments, and that you left out some of the MAGICE data because you had REPT instead. Just as a curiosity, do you think there could be any interest in including the same energy range across 2 different data sets, given that, you know, maybe instruments have different calibrations and stuff, and that maybe the data wouldn't match up exactly over that range? And if the model could maybe produce, well, I guess it would be hard to include 2 data sets for the same energy, but just wondering if you could shed any light on if it could reproduce both spectra, I guess.
Yeah, so the thing is, for MAGICE channel, it's for the higher energy. It's not like REPT is separated in very good range. So it's like 2 to 4 MeV. I remember it's like in a large, like the resolution for the energy channel is actually much higher. And since the wrapped channel, like the wrapped team is very good and they calibrated the data set and the performance of that data set is very good. That's why we don't use the MyGuide data. But yeah, I do agree. It's always good to check different instruments. And that's actually the spirit of like 2 1 probe, which like they can use A and B to calibrate with each other.
Right, yeah.
And one thing I want to mention is that we have, in this study, we want to use A and B. So it's like, okay, if your data is only available on A, but it's not available on B, we won't use that channel. The reason is that we want to capture the MLT dependence, right? And imagine you got 2 satellites flying around the Earth instead of 1 satellite, which definitely the previous one would have a better performance. That's why we choose the data set like available on both satellites channel.
Yeah, that makes a lot of sense.
Any final questions for Donglai? All right, I don't see any chat. I just wanted to take this opportunity again to thank Donglai again for his wonderful talk, and really appreciated you coming here and speaking to us about this. I also just like to thank everyone here for coming and attending. We will make sure that the recording for Donglai's talk will be uploaded to our YouTube channel, and the link will be there for you to come back and look for it whenever you'd like. And I'd also like to mention that our next GeoDAWG seminar will be on March 7th, given by Lucas Tarr and James Leake on their solar work. So be on the lookout for announcements in the SPA newsletter and other associated newsletters for that announcement going forward. And we look forward to seeing you then. Hope everyone does well, and we'll see you soon.
Thank you.
Thank you.
Thanks, Donglai.